Morning, sir. My name is Saitya from Tribly Department. Subject Power Electronics. Subject code AEED17. Assignment topic: Evaluate IGBT switching losses in high power inverters used in metro rails transactions traction systems and propose cooling solution. Evaluation of IGBT switching losses in metro rail traction system. Analysis and cooling strategies for high power inverters. Objective, scope, significance, structures. Objective: evaluate switching losses in insulated gate bipolar transistors (IGBTs) within high power traction inverters used in metro rail system and propose efficient cooling method. Scope: focus on switching phenomena, thermal management, and comparative cooling technologies relevant to rail traction applications. Significance: minimizing switching losses directly enhance inverter efficiency, reduce maintenance cost, and extend IGBT modules lifespan in demanding metro environment. Structure: presentation including fundamental of traction inverters, losses analysis, quantitative evaluation, and innovative cooling solutions. Agenda: structure of presentation. Introduction and objective. Overview of metro traction inverter systems and the importance of IGBT performance in high power environment. IGBT losses mechanism. Distinguish conduction losses from switching losses with focus on high frequency inverter operation. Loss evaluation and impact. Quantitative analysis of IGBT losses, thermal stress and reliability applications of for metro traction, cooling strategies, investigation of air and liquid cooling techniques, design consideration and thermal optimization, case studies and a future outlook, real world example of traction inverter cooling and discussion of ISCs and GAN innovation. Introduction: Metro rail traction system and inverters. Foundation of modern electric mobility. Metro rail electrification. Modern metro system uses electric traction powered by DC or AC overhead lines converted into regulated DC link voltage for inverters driving traction motors. Role of traction inverters. High power inverters convert DC link voltage into variable frequency AC to control asynchronous or permanent magnet synchronous traction motors. System requirement: traction inverter must achieve high efficiency greater than 95%, fault tolerance, low electromagnetic interference, and compactness due to limited onboard space. Integration with train control. Inverters interfaces with train control system for acceleration, regenerative braking, and safety interlock, requiring robust communication and monitoring. These four are the foundation of modern electric mobility. Roles of IGBTs in traction inverters, switching backbone of modern metro drive system. Function of IGBTs, operation range, advantages in traction module integration. Function of IGBTs: insulated gate bipolar transistor combines the high current capability of BJT with the fast switching of MOSFETs, enabling efficient DC to AC power conversion in traction drives. Operating range: traction grade IGBT typically handles voltage from 1.2 kV to 6.5 kV and current up to 1.0 amps. Switching at frequency between 1 to 10 kHz depending on inverter topology. Advanced in traction, high efficiency, boost on and controllability under wide load. Variation make IGBT ideal for accelerating, cruising, and regenerative braking models in metro systems. Module integration: IGBT are often packed into multiple chips modules with free wheel diodes and temperature sensors to provide power density and simplify thermal design. Loss mechanisms in IGBT: conduction versus switching, understanding energy dissipation in traction inverters, conduction losses, switching losses, dynamic behavior, in energy per cycle trade-off consideration. Conduction losses occurs when IGBT conducts current during the on state. These are proportional to collector current and voltage drop and dominate at high load current. Switching losses generated during traction transition system between on and off state due to overlap of voltage and current determined by switching frequency, voltages and current slopes, dv by dt and di by dt. Dynamic behavior turn on and turn off losses varies based on gate resistance, temperatures and stage inductance in the inverter circuit. Energy per cycle each switching event decision E on and E plus E of energy. Total switching losses in the product of this and switching frequency FSW. Trade-off consideration. High switching frequency reduces motor ripple but increases switching losses and thermal straits, necessitating optimization, gate control and cooling. Switching losses in high power inverters, key drives, influencing factors in metro traction system. Switching frequency. High switching frequency improves motor current smoothness but proportionality increases switching energy losses. DC link voltage and current. Switching losses scales with applied voltage and current amplitude. Metro system typical operator 750 volts to 3 kilowatt DC link level. Device architecture. Trench field stop IGBT software reduced the tail current and faster switching than planar type, lowering switching energy. Parasitic elements. Inductance and capacitance in inverters layout causes voltage overshoot and oscillations, aggravating energy losses during transition. Temperature dependence. An elevated junction temperature greater than 125 degrees carries mobility and switching charges increases resulting in higher switching losses. Quantitative evaluation of switching losses in traction application. Empirical and simulation based assignment. Experimental evaluation, total power dissipation, thermal impact simulation validation, comparison by technology. Experimental evaluation, switching losses test under 1.5 kV 600 amps consideration show typical per cycle energy 25 to 35 microjoules for modern 3.3 kV IGBT head to 2 kHz switching frequency. Total power dissipation for an inverter switching to kHz with 6 IGBTs. Total switching losses reaches approximately 300 to 400 watts per module depending on the duty cycle and temperature. Finite elements and circuit level simulation align with experimental data validation electrothermal models for inverters optimization. Duct cycle variation. Metro operation involves frequent acceleration, costing, and braking cycle, resulting in dynamic thermal loading on IGBTs. Regenerative braking energy recorded during braking increased inverter bidirectional power flow, elevating switches activity and flow symmetric across modules. Ambient condition. Underground tunnels and confident incomplete restrict airflow causing ambient temperature to exceed 45 degrees stress cooling system. Reliability and maintenance. Continuous service demands greater than 99.5% availability necessity inverters, channels, and predictive thermal monitoring system. Voltage standard typically traction supplies level range from 750 watt DC to 1.5 to 3 kilowatt DC intercity, direct influencing inverter stress and IGBT selections. Thermal impact of switching losses and reliability on managing junctions temperature for long-term performance. Junction temperature rises, thermal cycling effect, reliability degradation, packing constraint, monitoring and diagnostics. These five are the managing junction temperature for long-term performance. Cooling solution overview for high power IGBT module. Balancing thermal efficiency, cost and reliability. Air cooling system, liquid cooling system, two-phase cooling, heat pipe and vapor chamber, integrated thermal interfaces. These five types are the balancing thermal efficiency and cost reliability. Cooling solutions overview for high power IGBT modules. Design consideration for cooling in metro traction inverter. Optimization thermal management under system constraints. Space and weight limitations. Vibrations and shock resistance. Ambient and environmental conditions. Maintenance accessibility. Cooling fluid compatibility. Advanced cooling technologies, two-phase and hybrid system. Two-phase vaporite replace the latent heat of vaporization in dielectric fluid to maintain constant temperature operation, improving thermal uniformity. Vapor chamber integration hybrid system, dielectric fluid benefit research and trend. Comparative analysis of cooling methods, thermal efficiency, system complexity, maintenance requirement, reliability and longevity, cost and integration. Optimization strategies for loss reduction and cooling integration. Enhancing efficiency in metro traction inverters design, gate drives, optimization, soft switching techniques, advanced thermal interface material, integrated thermal electric design, digital control and monitoring. Thank you.